In this lesson, we're going to introduce ourselves to exponential functions and how they can apply to real-world situations. We're also going to be able to determine when a function represents exponential growth or exponential decay. Let's start with this warm-up. Consider each scenario described. Is this an example of exponential growth or decay? What is the rate of growth or decay? The first one, Mr. Stuhlfoth purchased his Kia Telluride for $38,000. The next year, according to the Kelley Blue Book, his car is worth $35,580. So this is an example of exponential decay. We know it's decay because the value is decreasing. And in order to figure out what the rate of decay is, you are going to take the current amount, $35,580, and you're going to divide that by 38,000, which is what your previous amount was. And when you do that, you find out that it has a rate of decay of, you find out that the value of the car is 0.9394. So this right here is not the amount that it's not the rate of decay. So this is telling you how much of the car how much of the value you have left. So this is the remaining value. And so if you think about this, if you only have 94% of the value remaining, this would mean that you had a rate of decay of 6%. And the way that you figure this out is you know that you had 100% of the value. So if you represent 100% as a decimal, it's just 1. And then we know it's decay, so we're subtracting whatever the rate is. And then we know that when we do that, we have 94% of it left over. If you solve this equation for R, you would end up with R equals 0.06, which represents a 6% decay. In the second example, Ms. Kosak deposited $1,500 of Christmas money in the bank. The next year, it is worth $1,537.50. So this would be an example of exponential growth because the new amount has increased from the previous amount or from the initial amount. And in order to figure out what the rate of growth is here, we would take the current amount, $1,537.50, and divide it by 1,500. And so when we do that, we have 1,537.50 divided by 1,500. We find out that we get 1.025, which would make sense because this is really saying that you have more than 100% growth, which means that you kept the money that you had and you increased it by 2.5%. So there's a 2.5%, which is equal to the rate of growth. And again, in order to figure that out, what you can say is I had 100% of my money. It's growing, so I need to add on to it whatever the rate of growth is. And when I do that, I know that I have 1.025. And so if you solve for R by subtracting 1, you get R is equal to 0.025, which is equal to the 2.5% growth that we said we had. So exponential functions are different than what we had previously been looking at in the past unit. Exponential functions are continuous functions with variables in the exponent. It is used to model growth or decay. So the important distinction between exponential functions and what we have previously been looking at is that the variable is in the exponent. That is how you're going to identify when you're dealing with an exponential equation. So let's take a look at this example that deals with a real-world example of depreciation. Most automobiles depreciate as they get older. suppose an automobile that originally costs $14,000 depreciates by 1/5 of its value every year. So a few things to take into consideration here. Depreciate means decay. That means the value is going down. Our original cost, our initial value is $14,000. So this is our initial value. And then we know that our rate of decay is 1/5. So this is our rate of decay. And again, 1/5 would be equal to 20%. So it's losing 20% of its value every year. So if we wanted to figure out the value of this automobile after 2.5 years, you could go the long way and you could find 20% of 14,000, subtract it, and then you have your value after 1 year. Then you could do the same thing for the second year, and then you'd have to do a half year. But what we really want to do is be able to get an equation for this. And so when we're writing equations, typically our exponential function for this would look something like this. Y equals A times B to the X power. And when we are dealing with these problems that have depreciation or appreciation for cars or any type of product, what we know is that this value for B really is going to be A times 1 plus or minus R raised to the X power. This plus or minus means whether it tells you whether or not you're using growth or decay. If you're growing, you're going to have 1 plus R because you want to have 100% plus the rate of which you're growing. If you are decaying, you'd have 1 minus R. A is going to be your initial value every time. So our equation for this would be our initial value of $14,000 times 1 minus 0.20 raised to the X power, or 14,000 times 0.8 raised to the X power. And so now that we have this equation that represents this situation, we want to know the value of the car after 2.5 years. So we would take this and we'd say f of 2.5 is equal to 14,000 times 0.8 raised to the 2.5 power. And so if we typed it into our calculator, 14,000 times 0.8 raised to the 2.5 power, you find out that this car after 2.5 years is only worth $8,014.07. So in the second part, it says, when is this automobile worth half of its initial value? So what we really want to figure out is we want to take our equation and say, well, when is it equal to $7,000? And so this type of problem, we do not know how to solve algebraically yet. We have not learned that. So when you are trying to find out, when the question is asking you when does something happen when you're dealing with these, what you're going to want to do is you're going to want to graph the two pieces of the equation. So you'd open up Desmos or whatever graphing calculator you're using. You would type in both equations, so 14,000 times 0.8 raised to the X power. I should probably put over here Y equals. And then the second part of the equation is Y equals half of that, so 7,000. And so then what we need to do is zoom out until we find out where we need to look. Actually, we can just adjust it. So we know our Y, let's adjust our x-axis to, we'll go -1 to, we'll go 20, we'll count by 2s, and then we'll adjust our y-axis to -10, and we'll go all the way, we need to go up to at least 14,000. So we'll go up to 20,000, and there we have our graph. And so now to find out where we want to look, we'd say, okay, where do those two lines intersect? And so you'll see that it tells us when x is 3.106, the value of this car will be $7,000. So the value, or when will it reach half its value, will be when x is equal to 3.106 years. So again, exponential functions. Exponential functions are going to be of the form y equals a times b to the x power. There are some important things to remember. B has to be greater than 0. The coefficient of a is your y-intercept, and the base b is the growth rate. So again, the y-intercept is always going to be a. This is also considered your initial value of any type of real-world problem. And the base is your growth rate, and b has to be greater than 0. So again, one of the goals that we want here is for you to be able to identify when you're dealing with growth or decay based on what a graph looks like or based on what an equation looks like. So when you're dealing with growth, what it's going to look like on a graph, it's typically going to be something like this. You'd have a graph that looks like this, where you're increasing over time. So this is going to happen when b is greater than 1. For decay is typically going to look like this. Where it's decreasing over time. And decay is going to happen when b is between 0 and 1. Again, b has to be positive, but when you have growth, b is greater than 1. When you have decay, b is less than 1. So if we look at this first example is going to be an example of decay. b is 0.95. It is less than 1. Our rate of decay, though, is going to be 5%. It's a 5% decay. And again, the best way to get this is to take, you know that this is decay, so you have 1 minus r, that's equal to 0.95. And if you solve for r, you get r equals 0.05, which is 5%. Over here, we see that this is going to be an example of growth. The reason it's growth is because 1.15 is bigger than 1. So to figure that out, we have 1 plus r equals 1.15. R, if you solve for it, it's going to be 0.15, so your rate of growth is 15%. It's growing by 15%. Here, that's 2, so this is going to, again, be growth. It is bigger than 1. And so at that point, you have 1 plus r is equal to 2. If you solve for that, r is equal to 1, so what you have is 100% growth. And finally, you have this right here. This is going to be decay as well, because b is less than 1. And if you want to find this out, you have 1 minus r. Since it's decay, you know that the rate is that b is 0.85. And so to find your rate, you find out that you have 0.15 when you solve for r. So your rate is going to be 15% rate of decay. So that is how you find out that. Now to find out your y-intercepts, remember your y-intercepts are going to be here. So in this case, the y-intercept is 12. The y-intercept is 2. The y-intercept is 0.025 or 0.25. And the y-intercept is going to be, in this case, normally would be 1, but then you're subtracting 1 so that everything is moving down. So your y-intercept is actually, in this case, going to be 2. So one other thing that you want to make sure you are familiar with is all exponential growth functions have a doubling time. That means that it's the amount of time that it takes for something to double. And then exponential decay have what is called half-life. And again, this time depends only on the ratio. So what that means is that it's going to, if the ratio is constant, it takes just as long to double 1,000 to 2,000 as it takes to double 5,000 to 10,000. So let's look at a couple more examples, and then you can get started on your homework. It says in 2006, there were 1,020,000,000 people worldwide using the internet at that time. The number of users was growing by 19.5%. It says write a model to estimate the number of people using the internet at T years, where T is the number of years after 2006. So again, if we're writing an equation here, you're going to have something that says f of t is equal to our initial amount, which is this large number, times 1.195, so that 19.5%, that's growing, raised to the t power. And so again, how did we get this? This is just 100% plus our rate, since it's growth. And so now that we have our equation, we're going to estimate the number of people using the internet in 2021. And so to figure out what you should plug in for this equation, you would take the year you're interested in, 2021, and subtract the original year, 2006. That gives you 15. So you know that t is going to be 15, so you'd like to find f of 15. That's equal to 1,020,000,000 times 1.195 raised to the 15th power. And what's going to happen when you type this in, because we have that number as being such a big number, is it's going to write it in scientific notation for us. And so we have 1.476 1101 times 10 to the 10th power. And so again, if you wanted to write that out, you'd have that 14,761,000 or 761,101,000 people using the internet. And so down here we have our initial value here would be 45. Our rate of decay would be 1%, or I guess that'd come right here. It's decaying by 1%. Here our initial value is 2. It's going to be growth, and the rate of growth is going to be 3.5%. And if we're looking at this problem, it says that they sold 450 cell phones. There is their initial amount. Sales have increased at a rate of 4.75%. Create a function that represents this situation where m is the number of months. So we'd have y equals 450 as our initial amount times 1.0475 raised to the m power. So again, this is just an introduction. You should be able to identify when something is growth or decay based on an equation, based on a situation, or based on a graph. And you should also be able to identify the initial value, or y-intercept, and come up with equations to represent a scenario given to you as a word problem. So go ahead and begin looking at the note or homework, and let me know if you have any questions.